This is Michael Obluda explaining my topics 5 through 12. And we're going to start out with water flowing in a stainless steel circular pipe of given dimensions and velocity, and it's asking for the pressure drop in the pipe. Right away, we know it's an internal flow question because it's asking for it's a circular pipe and it's fluid flowing in a circular pipe. And the assumptions we're making in this problem is that steady state, incompressible, the flow is fully developed, and there's no work devices in this case. And so the equations we're using is the extended Bernoulli equation. That is just energy balance per mass with friction in this case, because friction is a big factor in this pipe. And so one thing that's important to note is that there will be different friction equations or friction factor equations depending if it's laminar or turbulent. So right away we're going to use a Reynolds equation, rho v d over viscosity, to find if it's laminar or turbulent. In this case it tells us it's laminar, so we're going to use the laminar friction factor equation. Using that laminar friction factor equation we can find the friction, thus helping us finish the Bernoulli equation. Now we can find the pressure gradient. Now that we know the friction factor, or the friction, from the friction factor, we can find our pressure gradient for that problem. In the next part B, it says if the pipe diameter was increased to 1.6. So right away, that only part that changes is that it changes it to turbulent. If you calculate using the Reynolds equation, it's 11,000, which is over 10,000, making it turbulent. So this will give us a different friction factor equation. And with this different friction factor equation, we'll have a new friction and a new pressure gradient. Okay, next we have an underground aquifer, and water is being pumped from this aquifer 150 meters below, and it has a pressure gradient. There's a big difference in pressure, and there's a big, the pump is using 100 kilowatts of useful mechanical work. And right away we can assume this is a pump analysis extended Bernoulli kind of problem because it gives us a pump. That means there's work involved, and there's big height difference, so there's going to be some energy changes for sure. So using the Bernoulli balance, we know it's frictionless. We can assume it's frictionless. It's steady state, incompressible flow, and we know that P2 is twice of P1, and P1 is atmospheric, which in this case we got from handout 1. And then we got our other properties from table A9. So using the Bernoulli equation, we can cancel stuff out, and to actually get useful work into the equation, we divide it by mass times gravity to get it into H pump to find the head loss of the pipe, which is the friction. It's not frictionless, by the way. I did not mean to say that earlier. But to find the friction loss, the head loss, and from the height differences, we'll find that out, and the pressure gradients, and the pump, the head pump, we can find the head loss. All right. Next, we have a small spherical gravel with particle with given properties, and there's fluid flowing through these particles, and we have to estimate the minimum fluidization velocity for air going through these particles. And it's packed. This bed is packed with these particles, and it's also giving us our bed porosity, which is important. And if we look, some assumptions that we need to make is that steady state, it's incompressible, and then air is at 20 degrees in 1 atmosphere, giving us properties from our table A15. And the equations we're going to use for this one is this long one down here, and this is a very important equation in porous media. It will give us the interstitial velocity, which is the velocity that is flowing through a tightly packed bed very fastly. And that is what we're looking for here. And because we're finding the minimum velocity it can go through this to make the bed fluidized. So that is what we're looking for in this equation is Vs. So we have all the other givens, but it's going to look tough to solve. And so by using a quadratic formula, we can actually solve for V interstitial velocity, the minimum interstitial velocity to make the bed fluidized. Next, we have external a problem where there's particles falling from a bomb, the nuclear particles falling from a bomb because it exploded very high up in a plane, and it's asking how long will it take until the particles reach the bottom. So we know if it's asking for how long the particles reach the bottom, it's important to know the velocity because we know the height. So from the height and the velocity, we can find how long it'll take. So we're looking to find the velocity, and to find the velocity, The velocity is involved in a drag force equation that has to do with, I believe, it depends. You use two different equations if it's laminar or turbulent, but in this case we're going to use Fd equals 3 pi viscosity v diameter. And since we don't know drag force and we don't know velocity, we can't solve that right now. But if we use a force balance of the weight force and the buoyant force on the particle, we can find the drag force, and thus, so we get the drag force from the weight force and the buoyant force, and now we can solve for velocity. Once we have velocity, we can solve for the time it takes to get to the ground. And yeah, it's just, we know it's an external fluid flow problem because it's particles being separated falling from a high plane outside. Okay, next we have air that enters a diffuser at given properties, and we want to compare the speed of sound at the entrance compared to at the exit. And we know this is compressible flow because it's a ideal gas flowing at a very high speed. So the compressibility is actually significant, meaning the density will actually change. And some assumptions we can make is that air is ideal gas and it's going to have constant Cp. And if we're looking for C2 and C1, which are the Mach numbers, the speed of sound, and the speed of sound the Mach is compared to the speed of sound. So relative to the speed of sound, that is. So we're going to use we're going to use equations that we can find the temperature at the exit from the temperature at the entrance using a known K coefficient from air that depends on what ideal gas you have will change K. So using this equation, we can find the temperature at the exit, and the speed of sound is dependent on temperature and other constants. So then we compare the temperatures at the entrance and the exit to find the ratio of the Mach numbers, the speed of sound. Finally, we have a problem that asks for the velocity profile of a fluid flowing between two plates, and if it's asking for a velocity profile, we know that it is a Navier-Stokes procedure. So first thing in Navier-Stokes procedure is you want to do a mass balance and then a momentum balance to find your velocity, and then integrate and using boundary conditions to find your velocity profile. So we're going to start out by looking at our mass balance, our continuity equation, and there's lots of assumptions that are very important in canceling stuff out in these equations. So we'll go through them. All right, in the continuity equation, dp dt goes anything that has t in it, time dependence is steady state, goes to 0 because of steady state. And then in the problem statement, it says it's one-dimensional, so we know there's no velocity in the y or z direction. Those also go to 0. And then from the continuity equation, we can tell that dvx dx goes to 0. And so then that helps us with our momentum balance. In our momentum balance, we see that anything time dependent goes to 0 due to steady state. We know that dx goes to 0 due to the continuity equation. Any vx goes to 0 due to the continuity equation. It's one-dimensional. Vy, vz go to 0. And then we know that that z is x is not a function of z because it's very wide. So we know d squared, dz squared goes to 0. And then dp dx is a constant pressure gradient, so we know we can use delta p over L in this case for that. And it's incompressible Newtonian fluid, so the density and viscosity are pulled out of the continuity and mass balance. That's important to note too. And so finally, we're given just a second derivative is equal to the pressure gradient with viscosity and length under it. And if we integrate twice, we can get our velocity profile, but only if we have certain boundary conditions. And the boundary conditions that are very important that can help us solve for the integration for this is, the first one is that it is parallel, meaning there is no flux. It is the middle of it's like a parabola flow. There's no change. There's just no flux. It's symmetric. At x equals 0 is when it's going the fastest. And so we know dv, so we can solve the first integration and get one of our constants. And then to get the second constant, we use no slip at both walls, which happens for any solid fluid interface, and thus giving us our final velocity profile.